What we're going to show now is the power on sequence for the Picotronix. So I'll be doing a reset. The first thing you see is our Picotronix logo comes up. The next thing is that we go to a menu and the A button takes you to a list of virtual instruments. The design of the software is such that you have a selection of virtual instruments and each one does a different job. So instead of trying to put all of the functions into one piece of software, we have separate modules which implement a virtual instrument. So you can see here we've got multimeter, 2-channel DSO, logic analyzer. The ones underneath in purple are actually simulation modes, so you can go in there and see more or less what they do. So for example, with the multimeter, the other feature is that each virtual instrument has a help screen, and that is implemented as a JPEG image. So if I press the A button again, I'll get the help screen. That tells you what the buttons do, some information about how it works. There may be more than one help screen for a particular virtual instrument, in which case pressing the A button will cycle through the pages and eventually then take you back to the main menu. So for this case, we're going to go and show the Premier virtual instrument, which is the 2-channel DSO. So I'll use the buttons X and Y on the right hand side to select one of the menu options, and then the B button on the left lower corner of the LCD effectively activates that module. That takes us to the DSO, and the next thing we have to do, you see at the bottom there's a set of options and instructions. The one on the left, set, takes you to a higher level of menu where you can set things like trigger polarity, trigger source, types of display, various things like that. This one, the second button, is the run button, which effectively either starts the DSO, stops it, or in single shot mode it fires off a single trace. The next one is a set of variables which you can cycle through by pressing the button, and that lets you set up various parameters. And the two right hand buttons, the yellow and the green, allow you to go up and down through menus. So first of all we'll press the run button, and there we see we've got the waveform, and so we can change the frequency to get a different wave shape. We'll adjust the Tektronix to match it. So there we're seeing on channel A. Channel A is 2 volts per division. The Tektronix is 500 millivolts per division, so we'll put that to the same thing. And there we can see channel A is matching channel 1 on the Tektronix. So the next thing we will do is that we will go to the third button, and that lets us, at the moment this will let us select the trigger level. So if we press that, if we press these buttons here, we momentarily see the position of the trigger, which comes up as a brief horizontal cursor. So while you're actually moving the trigger up and down, you see it on the screen. When you stop moving the trigger, it goes away. The next one in this is channel A range, and that lets you change the vertical sensitivity of the trace. So we'll adjust that to the next one, which is 1 volt per division, and you can see that the signal is now bigger. And we can do the same thing on the Tektronix. So the next thing we're going to do is we're going to actually activate channel B, because if you see on the Tektronix, we've got channel B, or channel 2 in that case, is showing us the digital waveform, which is the base frequency of the signal generator. So to get to that menu, we're going to press the Set button. When you press the Set button, the bottom bar goes grey and the function of the buttons change. So in this is like a meta menu, and what this does is that the first button allows you to select the channel. So at the moment we're looking at channel A. So we'll press that. That takes us to channel B. So the next one is A/B, which is effectively like an alt mode. What it does is it captures channel A, then it captures channel B, and it displays both of them. So you have two trigger events. The next one is interleave. So in this mode, what we're doing is that we're going through with the ADC and we're capturing a whole buffer, but the ADC in the Pico is being programmed to swap between channel A and channel B. So every second sample will be the other channel. It then disentangles those and displays them, but as you can see, we're seeing the two waveforms which correspond to what we're seeing on the Tektronix. And again, we can change the frequency and see that it matches. We'll go to sine wave, triangle wave, and square wave. So the goal has been to try and make the display on the Picotronix match what you see on a typical laboratory bench scope. Now obviously the Picotronix cannot match the Tektronix at the very extremes, because the Tektronix has a 1 gigasample converter in it, and it also has, I think, 20 megapoints of memory and very fast DSP. So it's always going to be faster, but for an entry-level scope, most people want to see nice, clean waveforms, and they want to have triggers that work, being able to select between what the instrument is triggering on, the rise and the fall, and see a nice clean signal. So we'll go out of this mode now. So we're back to the option one. So channel A range, we've changed that to 1 volt per division. And now what we'll do is we'll go on channel B range. We'll leave that as it is. The next one is channel A ground. Now what that does is that steps the zero offset of the channel up and down, much the same. The Tektronix has got a knob, so on the Tektronix we can do this and see the cursor at the left is moving up and down. So what you're doing is you're shifting the 0 point of the waveform. So on the Picotronix, because we're slightly limited with our buttons, we haven't got knobs. In that case, what we can do is we can adjust the ground in whole divisions. So if I do this, you can see that the waveforms move. Now you might notice as well that we've lost our trigger. That's because we're triggering on channel A. So what we'll do, we'll go back to the set menu, and over at the right we've got the trigger select. We'll select channel B. So now we're triggering off channel B, and so channel A, it doesn't matter where it is because it's nice and stable. The red button is usually the exit button, so when you want to access the higher menu you push the red button, and then when you want to get out of it you push it again. So we'll move this back up so it's pretty much the same. We'll put the Tektronix the same way as well. So the next one we'll go to is time base. Okay, so time base allows us to select the time per division. So what this will do is that in the signal processing Pico, it will actually process the contents of that's captured by the ADC in a different way, and in the case of slow time bases it will have to decimate the large number of samples, and in the case of higher sample rates it will actually interpolate so we get a decent sort of a signal. So let's go through. We'll go down to the slow range first. So we're down to 2 milliseconds per division. We can go one further, we can go to 5 milliseconds per division. And so what we have to do now is that we have to change the frequency of the signal generator so we can actually see a waveform, because at these slow time bases 2 kilohertz is too fast. Okay, so there we're down at about 32 Hertz. So that's the sort of time base that you would use if you were looking at things like 50 Hertz noise, low audio, various signals that are down in the sub 100 Hertz bandwidth. So one of the things to notice with this is that on the Picotronix is actually capturing a lot more samples because it's capturing in 500 kilosamples per second. And so what it does is that it takes large groups of samples and averages them, but in addition to that it finds the minimum and the maximum excursion over that period, and it displays those as a light phosphor display. Now, to demonstrate that, what we're going to do is that we're going to decrease the amplitude of the signal way down, and then what we're going to do is that we're going to go to the channel A range and move it up so it's amplifying the signal a lot. So now we're on 1 volt per division. We can go up we can go up there to 100 millivolts per division. So what you'll see both the Tektronix and the Picotronix are showing that there is a noise floor on this signal, and so the Tektronix is capturing many more cycles because it's much faster, so you're seeing that as a fuzz. But on the Picotronix you're actually seeing the same noise, it's just that you're not seeing as much of it. So an interesting thing here is that on that range of 100 millivolts per division, we're actually doing some tricks. We actually take the 12-bit of the ADC and we're actually moving it up to 16 bits, and then we're actually doing an averaging and also finding the min-max, and when it's drawn, the noise, if you like, is drawn as a sort of a lighter background color, which is like phosphor. And if you see, the main triangle trace has been filtered and averaged, so it's looking quite solid. So we're seeing a solid triangle. So another point to note there is that the ADC in the 2350 is quite happy. We're using 200 steps of its 4096 steps. So we're only using 5% of its total range to actually track that triangle wave, and the quality of the triangle wave when it's averaged is actually very good. So we can switch to a sine wave to check that. Same thing. And so from a functional point of view, what we're seeing on the Picotronix is giving us a picture which is effectively the same picture as the Tektronix, although the Tektronix can obviously capture a lot more samples and show more detail than we can, because we're limited in our frame rate because of the Picos are powerful, but there's a limit to what they can do in a particular cycle. So we move back up to a high voltage, and again you can see, an interesting thing you might see there is that on our display, what we do is that we display vertical lines as faint lines, and we display actual sample points as dots. So you get a nice picture of the waveform, but you can also see exactly where the samples are. So we go back to 1 volt per division, and we're seeing the same sine wave. So we'll just go up and look at some faster signals now. So with the time base, we'll move up from the slower speed where we're looking at at the moment 32 Hertz. So there we are at 50 microseconds per division, which is much faster, and we're going to have to put the signal generator up. Okay, so there we've moved up to 3.5 kilohertz. The Picotronix is 50 microseconds per division, and the Tektronix is 40 microseconds per division. But again, we're seeing a stable trace. We're seeing both the channel A and the channel B. So we can move up a couple more steps. For the base level instrument, at the moment we're stopping at 10 microseconds per division. Later on we will activate ESR, which is effective sample rate detection, and probably move up so we can look at signals up to about a megahertz. But the other solution is that Picotronix is expandable, so on that connector on the right we can actually plug in a much faster ADC. So we have a board which you see there. That board plugs in and it gives you a logic analyzer, and also it's got a 100 megasample ADC on it. So, just as a final thing, at the fastest sample rate, so we're looking there at 11 kilohertz, so we can go faster than that. Once we go past 20 or 30 kilohertz, we're starting to see some artifacts from the ADC, because it's doing a linear interpolation between the points. At that stage you have to start using different techniques or move to a faster ADC. But the ADC is maintaining the same noise levels at this, so I can turn the signal down. And then we'll adjust the vertical gain. So we're back at 100 millivolts per division. So the ADC is again only using about 200 steps of its range. So that's 5% of its maximum 0 to 3 volt range. And it's still tracking the signal, and we're getting quite a good signal. So we'll just move to a triangle wave. You can see it's a triangle wave. It's got a few artifacts and so forth, which are caused by the sample rate, and also there will be some, some perturbations in the signal at this frequency and this range, because we're looking at, again, we're just looking at the bottom 5% of the ADC range.